And I'm going to share the screen. And we're going to go out to the D2L course. And we're going to begin Unit 3. And there are going to be really about 3 primary topics within Unit 3. One of those, we're going to kind of shorten some information. We're going to limit what we talk about. I've left all the detailed information in there, but I'll pick and choose. So again, you may want to make notes as you go. But the 3 primary topics are going to be quadratic functions, long division, rational functions, and then we're going to talk a little bit about polynomial functions. At the moment, there's lots of information in there about polynomial functions. That's the one topic where I'm going to be selective about the material. Having talked with my colleagues who teach calculus, there are certain concepts that are more important than others related to polynomials, and so we're going to focus on those because, again, one of the reasons for college algebra is to prepare you for pre-calculus and ultimately the calculus sequence. So we're going to be selective, about which part. So today we're going to begin our discussion of quadratic functions. So I've logged into D2L, and on the right hand side I'm going to scroll down to Unit 3. And I'm going to open the folder labeled quadratic functions. That's going to be our topic for today. And you should see 2 documents. The first one is labeled quadratic functions. And this is kind of a Word document that summarizes quadratic functions that I have used in the past with my classes. What we're going to view today as we're having this discussion is the quadratic functions virtual. That's a PowerPoint that we're going to kind of walk through together, and I will add some things too as we go. So you may want to open that up, but I'm going to be sharing my screen. So you should be able to view that. So this topic is quadratic functions. And I really want to begin with a video, which seems kind of weird since we're in this virtual format, but I want us to look at this video because it gives you an idea of the uses of parabolas and where you might encounter parabolas, again, to give you a sense of the applications or why you want to learn about this. And this particular video was made by an instructor in Canada. So he does reference some landmarks in Canada, so that might be a little confusing or interesting to you. So I'm hopeful that this will play. I haven't tried it in this Zoom format, so let's see how it works. Yes, we're going to play. Okay, my computer's actually a little slow, so give it just a minute. All right, let's try again. You're still thinking about it. And it's still thinking about it. Okay, so I hope that little short 3-minute video kind of gives you some insight into at least why we need to study parabolas. And a parabola, when you write its equation, is what we call a quadratic function. I want to define it and give you some information about the quadratic function. So the formal definition says let A, B, and C be real numbers with A not equal to 0. Now, to be a real number means that it can be any number you can think of that's on the number line. It can be positive, it can be negative, it can be a fraction, it can be a decimal. Okay, and it says then the function f of x equals ax squared plus bx plus c is called a quadratic function. And so we really have kind of talked about this before, and I'm going to kind of move out here where I can do some writing. But we've really kind of talked a little bit about this before, because earlier in the chapter, or in Unit 2, we talked about our basic parent graphs. And if you'll recall, one of our parent graphs was the squaring function, which in its basic form was f of x equals x squared. And they called it the squaring function because it has that exponent of 2, and you're asked to square it. Okay, and we also talked about the format where you have f of x equals a times bx minus h squared plus k, where we could use our transformations of graphs to move the basic squaring function left or right, up or down. We could reflect it on the x, reflect it on the y, vertically stretch it or compress it, or horizontally stretch it or compress it. And so one of the things that identifies it as the quadratic function, or the squaring function if you prefer that terminology, is that it has this exponent, or the high exponent is 2. Okay, so if you'll notice in this particular definition, our high exponent is 2. Previously, at the end of Unit 2, we talked about linear functions, and you need to be able to distinguish between them. For a linear function, you would often see f of x or y equals mx plus b. And one of the ways that we recognize that as a linear function is that our high exponent was an understood 1. Now, again, the 1 is usually not written. So, again, you need to be able to distinguish between whether something is linear or whether it's quadratic simply by looking at the equation. So, it's linear when kind of your highest exponent is 1. You have, just plain old x. And it is a quadratic function, or the squaring function, when that high exponent is 2. And again, from our earlier discussions, hopefully you remember that the shape or the graph of a parabola of a quadratic or squaring function is the parabola, centered at 0, 0. So this is our basic everyday parent function that I graphed here that we talked about in Unit 2. Okay, it's a U-shaped curve. Okay, and so this is the basic graph of f of x equals just plain old x squared. As was true with the linear functions, it is also true with the quadratic functions that the domain, all of the possible x values for a quadratic function, is all real numbers from negative infinity to positive infinity. all parabolas, one of the new characteristics that you may not have seen or recognized before with a parabola is that they are all symmetric, okay? Not necessarily symmetric to the y-axis or symmetric to the x-axis, but they are symmetric. It's kind of that there's this imaginary line that if you fold the parabola across that imaginary line, it appears to be the same on the left side as the right side. That axis of symmetry, as they call it, or line of symmetry, always goes through that center point. So on our basic graph, our axis of symmetry happens to be the y-axis. Okay, so our axis of symmetry would be the vertical line x equals 0 for this particular parabola. But it doesn't always have to be 0, but the deal is it does go through that center point. And again, if I could fold this graph in half, you wouldn't be able to tell the left side from the right side. Our relative minimum, which if you'll recall from previous discussions, is the point where the graph changes direction, and it's either a minimum or a maximum depending upon your graph. On our basic parent graph, that is this point right here, and since it's at the bottom, this would be our relative minimum, and it has a fancy name because it is an important point of the parabola, because that's the point where it changes direction. The special name is that point is called the vertex. And for our basic parent graph, that vertex is at the origin, which is 0, 0. And again, we really have already been dealing with the parabola in this format, okay? The format that we looked at previously, this f of x equals a times the quantity bx minus h squared plus k, is called the vertex form. And it's called the vertex form because I can very easily look at it and tell you what the vertex would be. The vertex, if we think about it in this vertex form, we usually use the capital letter V for stand for vertex, would be my H and K. Remember, H corresponds to my horizontal translation, so I have to tell how many I moved left or right. And then also the K is my vertical translation. So I can find the vertex, that point where it changes direction, by looking at my horizontal translation and my vertical translation. You do have to be careful, again, to watch your signs, and your axis of symmetry is going to be a vertical line, x equals h. Okay, so I want to kind of go over to a Word document, and I just want to look at an example like we were doing earlier in Unit 2 related to this quadratic, so that hopefully we can make some connections here a little bit later as we go. So let's say, for example, we have the problem f of x equals -2 times the quantity x minus 3 squared plus 1. Okay, and so if this were a question on the test, remember I would have asked you, what is the vertical translation? What is the horizontal translation? Is there a reflection on x? Is there a reflection on y? And then is there a vertical stretch or shrink or compression? So if you'll remember, the first thing we would do is identify the different values. You have A, which is the number out front. B is the number inside the parentheses with the X. In this case, is an understood 1. H is the number inside, and then K is the number tagged at the end. Good little review for us. Remember that the vertical translation is determined by K. And since K is +1, we're going to go up 1 unit. My horizontal translation is determined by H. Okay, but we want to avoid a sign error, so I'm going to go off over here to the side. X minus 3 equals 0, and I'm going to solve for X. So X equals 3. So it's a positive 3, so that tells me I'm going to go right 3 units. Reflection on X is determined by the sign of A. A is negative, so there would be a reflection on X. Reflection on Y is determined by the sign of B. B is positive, so there's no reflection on Y. And then finally, in terms of our vertical stretch or compression, that is determined by the numeric value of A, which in this case is a 2, which is bigger than 1, which means we have a stretch. So it is stretched vertically. Now, I go through all that to get to this point. Okay, if you look at this vertical translation and the horizontal translation together, that's going to give us our vertex. Because if I go to graph this particular equation, and let me see if I can draw us a grid. Okay, if I think about what the basic parent graph originally looked like, remember our basic parent graph is centered at 0, 0, and it's going to be that U-shaped curve. And so on this particular one that I'm trying to graph now, I want to go up 1 and right 3. So I'm going to begin at that relative minimum, which is at 0, 0, and I'm going to go up 1 and right 3. That's kind of my new center point, and it's at the ordered pair 3, 1. Right 3 is a positive 3, up 1 is a positive 1. So this gives me my vertex. It also tells me I'm going to reflect on the X, which means this parabola is going to flip over, and it's going to be stretched vertically by 2. So I can kind of get an idea. Let's see if I go 1, 2. Okay, I can get an idea, and it may not look as skinny as perhaps as it should, but you get an idea that it looks this way. Now, one of the things that they often ask about parabolas is it asks about the direction of the opening. In other words, they want to know, is your parabola turned upwards or is it turned downward? Which really, quite honestly, goes back to whether or not you have a reflection on X. Okay, so they're really asking you questions in a different way, and you really already know the answer. So the reflection on X is, now they ask about it in terms of the direction of the opening. And again, they're wanting to know, does the parabola, the options are that it opens up or it opens down. And so let's make us a couple of notes here, because we really already know this, but it's not necessarily been formalized for us. It opens up when there is no reflection on X. There's no reflection on X when A is positive. It opens down if there is a reflection on X and our A is negative. Okay, so that's how we're going to make the distinction between whether it opens up or opens down, which is the terminology that they tend to use in the text. And again, it opens up similar to our parent graph here when there's no reflection on X and A is positive. It opens down when there is a reflection on X and A is negative. Now, hopefully that most of that information there's a little bit of new stuff there, but for the most part, that should be review information. So let me see, pause for a minute and see if you have questions. And if you're putting them in the chat, I've got to pull my chat up, so give me just a minute. It'll let me. Okay. Doesn't seem to want to let me. So do you have questions? You'll have to verbalize them for me. Okay. One other thing that I want to point out that's kind of the new piece here is identifying your axis of symmetry. So for this graph that we created of -2 quantity x minus 3 squared plus 1, my axis of symmetry has to go through the vertex. Okay, and so it's a vertical line, and a vertical line always has the format x equals whatever the x coordinate is. So the formula is x equals h, because h corresponds to my horizontal translation. So for this problem, my axis of symmetry is x equals 3. That would be the line that I would fold across. Okay. All right, let me go back to the PowerPoint. So that's the vertex form. And guys, it would be great and awesome if our equations were given to us in that format all the time. But unfortunately, they're not. More times than not, when you're dealing with quadratic functions or the squaring function, they're going to be given to you in this format that you see up here in this definition, where you have ax squared plus bx plus c. The a in that equation does correspond to the a that we've had over here in our other format. But beyond that, there's nothing else in common. And the downside to this format of f of x equals ax squared plus bx plus c is you really can only tell me about two things. And I believe I have that on the next slide. So I'm going to scroll to the next slide. That format, that f of x equals ax squared plus bx plus c, is called the standard form of a quadratic function, okay? And so I can really only tell you two things. One is I can tell you that it's a quadratic. And I can tell you that it's a quadratic because that high exponent on the variable is 2. So that's how I know it's a quadratic. Knowing that it's a quadratic also lets me know that visually it's going to be a parabola. And the second thing that I can tell you is based on A, I can tell you whether that parabola is going to open up or open down, because that value of whether it's positive or negative tells me whether or not it's going to open up or open down. But looking at this standard form of a quadratic function, I can't really tell you anything else. I cannot tell you anything about the key points, or at least the key point of the vertex. I cannot look at this standard form of the quadratic function and tell you the vertex. So that becomes a little bit of a challenge. One option we have is we can take this standard form and we can convert it to that vertex form that we were just looking at and using, and rewrite this as f of x equals a times bx minus h squared plus k. Because to do that, you have to use this big, long, convoluted process called completing the square. Okay, so to get from the standard form of the quadratic function to the vertex form, you have to use what's called completing the square. And honestly, it's awful. It's a lengthy process. It's confusing. And it's just not worth the effort. Okay? So lucky for you guys, we're not going to do that. There is another process, and we're going to talk about that as we go, because more times than not, you're going to be given the quadratic function in standard form. And again, all that form is going to tell you is that, first of all, it's a quadratic because the highest exponent is 2, which means visually you're going to have a parabola, and then you're going to be able to tell me whether that parabola opens up or opens down. Now, guys, I can't see the chat. I can't see your faces. So if you have questions, you have to speak up for me, because otherwise I can't hear you. Just like we were in class, you can interrupt me. Doesn't bother me. Okay, I'm not seeing anything in the chat right now. Okay, I believe on this slide that I have here, I'm on slide 5. I basically walk you through what I was just telling you about the letter A. That letter A is called, in mathematics, is called the leading coefficient. Okay, so the letter A here, which is the number in front of the x squared, is called the leading coefficient. Coefficient is the name mathematically for the number in front of a letter. And it's the leading coefficient because it's out front, it's in the lead. If you'll notice that when you write a quadratic, you have the highest exponent first, so you'd have the x squared term first, then you have the x term, and then you have the constant. This is called descending order. We typically write functions in descending order of exponents. We do that even with linear, because with linear we would write f of x equals mx plus b. Remember that understood one is there, so you have the highest exponent variable first, then you have the constant. So we do the same thing with a quadratic. You'll find that even when we start talking about other type functions where maybe you have something to the third power or the fourth power, if you have something like ax to the fourth plus bx to the third plus cx squared plus dx plus e, we still write it in descending order of the exponents. We start with the high exponent and work our way down to the lowest. So in each case, the coefficient in front of that high exponent, whether it's a or m, is called the leading coefficient. And again, for our quadratic that we're focusing on, as I mentioned to you just a minute ago, that determines the direction of the opening. It still also determines whether or not you have that vertical stretch or shrink using the same guidelines that we had previously. If A is greater than 1, it's stretched. If A is equal to 1, it's standard or the same. And if it's between 0 and 1, so that it's a fraction like 1/2 or 2/3, it does have a shrink. So you could also get a sense of, has it been stretched or compressed? Okay, questions? Okay, moving on then. All right, so let's think about the key points on a parabola. Okay, think about the key points on a parabola. One of the most important points on a parabola is the vertex, because remember, as I just mentioned to you a few minutes ago, that vertex corresponds to the relative minimum or the relative maximum. So it's the point where the graph changes direction. So that lets you know, okay, where should I start turning my curve? You know, should I start turning it? Where should I change from going up to going down, or from going down to up? So that vertex is an important point, because that kind of gives you that relative minimum or relative maximum and where you should turn around. Now again, if you have the vertex form, you can look at your horizontal translation and your vertical translation. But guys, again, we don't really get that very often. And I really don't want to have to go through that long, lengthy process of completing the squares. So the very best way and the easiest way to find the vertex for a parabola is to use what we call the vertex formula. Okay, so here's the vertex formula. If you have your equation, and it's written there on the slide, but I'm going to kind of write it off here to the side of the screen too, so that you can see it. Okay, if you have your quadratic, whoops, sorry about that. Let me get back. Okay, if you have F, and it's doing something funky, hold on. Okay, so if you have your equation f of x equals ax squared plus bx plus c. Okay, so that's your quadratic equation in standard form. you've got to eventually find, for the vertex, you have to have an X value and a Y value. Again, we normally refer to those as H and K. Okay, so to find the X coordinate of the vertex, okay, so to find the X coordinate, which we often call H, we're going to use the formula opposite of B over 2A. And again, I have that formula written over here to the side. Okay, so to find the H coordinate, which is the X value of the vertex, we do the opposite of B over 2A. And A and B come from the formula itself. To find the K coordinate of the vertex, which corresponds to the Y, or f of x. Okay, remember y and f of x are interchangeable. You basically substitute the x value that you found into the formula. Okay, so we substitute x into the given function and solve to find the y coordinate. And we're going to do this in a minute together with some numbers. Okay, but you need to know the vertex. You need to know the vertex because, again, that's going to tell you where the graph bottoms out or where it tops out. The other key points we've talked about before with other functions, but they also include the y-intercept. Where does the equation cross the y-axis? And again, I'll remind you what that would look like. Okay, so if we're thinking about our parabola, okay, and I'm just going to randomly draw one here. If you look at a parabola, you're wanting to know where it crosses the y-axis. Okay, so this point here where it crosses the y-axis would have the ordered pair 0 and some y value. Okay, and so that's the y-intercept. The y-intercept is where it crosses the y-axis. To find it, it's the same process we used all semester. We let x equal 0 and solve for y. We also want to be able to find the y-intercepts. And we've talked about this before, how that phrase y-intercepts, there are different verbs or different phrases that can be used. So we can talk about X-intercepts. The common term is we call them zeros. This is probably one you'll see a good bit. They can also be called solutions. And I've even seen the word factors used. And so those four words are interchangeable. Okay, and so it depends on which textbook you're looking at, which textbook author. It may also depend upon who your instructor is. And so to find zeros, again, if you want to see what that looks like visually, what are we trying to do? Again, just to remind you, never hurts to see it a couple of times. Apparently my neighbor has decided to cut his grass, so I'm sorry for the lawnmower in the background. Okay, so if we were looking at a parabola and thinking about finding our x-intercepts, we're looking for the point or points, in this case there's two, where the graph crosses the x-axis, and they would have the ordered pair. You'd have x1, comma 0, and you would have x2, comma 0. We reviewed at the beginning of the semester with quadratics and talked about how you could use factoring to find those x-intercepts or those zeros. Quite honestly, a lot of you didn't like that. And so the alternative method is to use the quadratic formula. You have to use the quadratic formula if the function doesn't factor. But guys, using the quadratic formula works every time, all the time. So if you're not good at factoring, or you just flat out despise that particular technique, then you can use the quadratic formula. This is one of the few formulas from mathematics that I would say is worthwhile committing to memory. Now, I do realize that for the test, you'll be able to use your notes, and so you'll have access to that formula. But again, it's kind of one of those that you use a lot throughout mathematics, and so it's one that would be helpful for you to know by memory. And there are memory devices to help you remember it. In fact, there's a little song that you might have learned in high school, or perhaps not, that goes like this. Negative b, plus or minus square root, plus or minus square root, b squared minus 4ac, b squared minus 4ac, over 2a, over 2a. So, you know, you can play back that little ditty and sing and whatever when you're trying to remember the formula while you're in the midst of taking the test. You can do that. I heard some of you laughing at me. That's fine. It's probably not the first time I've been laughed at. Okay, let me check the roster real quick. But do you have questions before we move on? We're going to get into some examples. I'm trying to take attendance, so hang on. Jocelyn. Okay, any questions?
Oh.
Shakita, are you laughing at me?
What is wrong with you, dude? Don't ever sing that song again, bro.
Is somebody else singing it?
Yeah, okay. Her name is Laura Rowson.
All right, so let's go back to our PowerPoint, and I want us to go through some questions together, some examples, and we're going to look at finding the vertex, finding the Y-intercept, finding the zeros, graphing it, looking at the axis of symmetry, and that sort of thing. So we're going to take a look at some examples next. Okay, here we go. Here's the first one. F of x equals negative x squared plus 2x plus 3. And honestly, it really doesn't matter where we begin, whether I start with finding the x-intercepts or the zeros or the vertex. Okay, it really doesn't matter. I just have a tendency, I guess, to do the vertex first, but it's really up to you, so you can really begin wherever you want. So I'm going to go off over here to the side, so I have lots of space, and I'm going to find the vertex. And to find the vertex, I'm going to use the formula. I do not want to, nor am I going to show you how to complete the square. Okay, so we're going to solely rely on the formula. And I'm going to write the formula down. For my x coordinate, it is the opposite of b over 2a. And to get the y coordinate, I substitute my x value back into the function itself. So I'm going to identify a, b, and c. A is always the number in front of the squared term, which in this case is an understood -1. B is the number in front of the x, and C is the constant. We're going to plug and chug. To get the x coordinate, we want the opposite of b, so we want the opposite of +2 over 2 times a, which is -1. I'm going to do the math. So I have -2 over 2 times -1 is -2. -2 divided by -2 is +1. So the x coordinate of my vertex that I'm looking for is a +1. To find the y coordinate, I have to substitute that value of 1 back into the original function. So when I do that, I have the opposite, or I have -1 times 1 squared plus 2 times 1 plus 3. So I have -1, 1 squared. 1 times 1 is 1. 2 times 1 is 2 plus 3. -1 times 1 is -1 plus 2 plus 3. Add and subtract left to right. -1 plus 2 is a +1 plus 3 is 4. So the y value of my vertex is 4. So my vertex is 1, 4. So I'm going to come off over here to the side, and I'm going to begin a sketch of my parabola, because I know eventually it's going to be a parabola. Okay, so I know that my vertex is 1, 4. So if I graph that ordered pair, starting at the origin, I'm going to go right 1 and up 4. Here's my vertex. If I think about the direction of my opening, which is a question I could be asked, the direction of my opening is going to be that it opens down because A is negative. That's how I know that it opens down. So eventually, I don't know exactly where, but eventually this parabola is going to be turned upside down on its graph. I then need to find the other key points. So I need to find the y-intercept. To find the y-intercept for any function, we let x equals 0 and we solve. So again, guys, it's a plug and chug. So I'm going to substitute 0 in place of x. So I would have -1 times 0 squared plus 2 times 0 plus 3. So I have -1 times 0 plus 2 times 0 is 0 plus 3. -1 times 0 is 0 plus 0 plus 3. 0 plus 3 is 3. So my y-intercept, written as an ordered pair, would be x, we write x comma y, and so it would be 0, 3. So visually on the graph, my y-intercept is at this point right here. The last piece that I need, and let me see if I can insert me an extra slide here so we have some space. Okay, so still looking at this example, I don't have room to do my X-intercepts here, so I'm going to go on to the other slide. Let me write down my function again. Okay, so my function is f of x equals the opposite of x squared plus 2x plus 3, let me make sure I write it down right, plus 2x plus 3. Okay, so it's the same equation, and now I need to find my zeros or my y-intercept. To find the zeros or my x-intercepts, we let y or f of x equals 0, and we solve. So I have 0 equals the opposite of x squared plus 2x plus 3. Now, if you prefer, you can factor. But I know what a struggle a lot of you had with factoring. So I'm going to work through this problem using the quadratic formula. Okay, so A is the understood -1, B is the 2, and C is 3. So using the quadratic formula, which is the opposite of B, plus or minus the square root of B squared minus 4AC all over 2A. One of the biggest mistakes that students make is forgetting to put the entire numerator over the 2A. So please be careful with that. And guys, then this becomes a straight flat out plug it in, plug it in. So I have the opposite of B, which is positive 2, plus or minus the square root of B, which is 2 squared, minus 4 times A, which is -1, times C, which is positive 3, all over 2 times A, which is -1. So I've plugged in the numbers. And then I'm going to come back and I'm going to do the math. Okay, so I would have, and I'm going to start over here off to the side, -2 plus or minus the square root. 2 squared is 4. Minus 4 times -1 is positive 4. Negative times a negative is a positive. Times 3 is positive 12. All over -2. 2 times -1. Then I'm going to come back and I have -2 plus or minus the square root. 4 plus 12 is 16 over -2. I have a radical, so I need to simplify the radical. 16 is 4 times 4. So I have -2 plus or minus 4 all divided by -2. Now, that is 2 answers there, guys, so be careful. Okay, so let's see what the 2 answers are. I'm not quite finished yet. Okay, so I would do -2 plus 4 all divided by -2. But I also have to do -2 minus 4 divided by -2. -2 plus 4 is positive 2 divided by -2 is -1. -2 minus 4 is -6 divided by -2. -6 divided by -2 is positive 3. So my 2 zeros, and you should have 2 because remember the highest exponent tells you how many zeros you should have. The highest exponent tells you how many zeros you should have. So I have -1 0 and positive 3 0 if I write them as ordered pairs. So I'm going to back up to my graph. And so I have a 0 at -1, and I have a 0 at 3. I know my opening should be down, so it's going to come up and look something like this. There's the graph of that parabola. if I were asked to find the axis of symmetry, remember the axis of symmetry has to go through the vertex, and it's a vertical line, so it's going to be x equals h, and we already determined that h, or the x coordinate, is +1. So my axis of symmetry is x equals 1. Okay, that's kind of the expectation, guys. You have to be able to find the vertex, the direction of the opening, the y-intercept, and the zeros, and the axis of symmetry. We can look at another example in just a minute, but do you have questions?
Go back to the other page so I can screenshot it.
Okay, I'm sorry. You got it?
Yeah, I know how to do it, but you know me, I gotta write it down later.
Okay, other questions?
Oh my gosh, can we skip this quadratic? I don't like this crap, bro.
I'm sorry, we can't skip it. Quadratic, probably linear is one of the most important, which we've already talked about. Probably the second one, if you were ranking them, would be the quadratic. It has, and again, the video at the beginning hopefully showed you a lot of the different applications that you could see related to parabolas. All right, let's see if we can take a look at another example. And then later on this afternoon, I'll post your homework within WebAssign if you want to start taking a look at it.
Are you gonna post this? Are you gonna post this like as a recording online?
I do have the record. I do have it recording, and I do plan to post it once it gets up, once it gets processed.
Okay, I have to leave. That's why I'm asking. You're gonna do another example,
Okay.
but I gotta go.
Yes, I'm going. I will have. It'll be posted probably later this afternoon, Shakita.
Sweet. I'll see you an email.
Okay. All right. So let's see if we can look through another example. We have about 25 minutes. I think we can maybe walk through it together before we have to sign off today. So the function that you're given here is f of x equals 2x squared minus 8x minus 3. And again, I initially recognize it as a quadratic because it has that high exponent of 2. And again, it really doesn't matter where I begin, but I tend to begin with the vertex. And again, I'm going to find my vertex using the formula. I don't suggest that you do it any other way. Guys, a lot of this is plugging and chugging. Okay, so you may want to organize your formulas together on one page. To find the x value of the vertex, the formula is the opposite of b over 2a. To find the y coordinate, we substitute x back into the original problem. I'm going to identify my a, b, and c. Remember, a is always the number in front of the squared term. B is the number in front of the x, and C is the constant. Okay, guys, if you'll make a note for me in the chat so I can refer to it later. If there's been any kind of audio issues today, would you please let me know that, and we'll so I can work with IT. If there haven't been any, just maybe put no problems or something like that so I'll know. Okay, so going back to my formula, we're going to plug and chug. Okay, so we want to do the opposite of b, and b is -8. So we need the opposite of -8 over 2 times a, which is 2. So the opposite of -8 is going to be +8 over 2 times 2, which is 4. 8 divided by 4 is +2. So the x value of the vertex is positive 2. If I'm going too fast, somebody speak up because I can't see your beautiful faces. I then, to find the y coordinate, have to substitute 2 back into the original function wherever there is an x. So I would have 2 times 2 squared minus 8 times 2 minus 3. And then I'm going to do the math. So I have 2 times 2 squared is 4 minus 8 times 2 is 16 minus 3. 2 times 4 is 8 minus 16 minus 3. So I have 8 minus 16, which is negative 8, minus 3, which is negative 11. So the y coordinate of the vertex is negative 11. And again, I'm going to go off to the side and begin my graph. Let me try that again because I need to move my graph up just a little bit. Whoops, jumped around on you, hold on. Sorry about that, got too close to the edge. Okay, so my vertex is at 2, negative 11. So starting at the origin, I'm going 2 to the right and 11 down. So my vertex is at 2, negative 11. Okay, then I need to think about the direction of my opening. Okay, so the direction of the opening, which we determine by looking at the sign of A. Okay, so when I look at the sign of A, it is positive, and so that lets me know that overall my graph is going to open up. I then need my other key points. So I want to find the y-intercept. You find the y-intercept of any function by letting x equal 0. So again, that's a plug and chug. I'm going to substitute 0 into the original function. So I would have 2 times 0 squared minus 8 times 0 minus 3. 0 squared is 0, so I have 2 times 0 minus 8 times 0 is 0 minus 3. 2 times 0 is 0 minus 0 minus 3 ultimately gives me the value of negative 3. So my y-intercept written as an ordered pair would be 0, negative 3.
I have a question.
Yes, ma'am, Madeline. Is it Madeline?
Yes. The C value, is it just these problems, like these two examples, or is the y-intercept just going to be the 0? I meant, yeah, is it just going to be the C value?
Typically, your y-intercept will be the C value, but just be careful, make sure you don't get the wrong sign.
Okay.
See, like the C value here is negative 3. And that's the case because you're plugging in 0 for x, which basically eliminates the first two parts.
What if you don't plug in?
There's no other way to find the y-intercept. You have to plug in z. But you can take, Madeline's pointing out a shortcut in that if you realize, oh, when I plug in 0, I'm just going to be left with c. So what we're saying is that if you want to think about it as a formula, your y-intercept in this case is 0c. Bless you.
Thank you.
You good, Madeline?
Yes, I'm good.
Z?
I'm good. Yeah.
Okay. So we found our vertex. We found our y-intercept. We know it's going to open up. So let's see if we can find our zeros. And again, I'm going to add a blank slide here so we have some space. So let me write it down. 2x squared minus 8x minus 3. Okay, so my function is f of x equals 2x squared minus 8x minus 3. Okay, so again, I need to, in this case, I'm ready to find the zeros. And to find the zeros, we let y or f of x equals 0. I'm sorry?
Not you.
So I have 0 equals 2x squared minus 8x minus 3. And again, I might be able to factor that, guys, but again, I know a lot of you struggled with factoring. So I'm going to use quadratic formula again. If you prefer factoring, feel free. A is positive 2, B is negative 8, and C is negative 3. I'm going to write down my formula. Opposite of B, plus or minus, square root, B squared, minus 4AC, all over 2A. Okay, so now it becomes kind of that plug and chug. So if I begin plugging into my quadratic formula, I have x equals the opposite of negative 8, which is the value for b, plus or minus the square root of negative 8 squared minus 4 times 2 times minus 3 all over 2 times a, which is 2. I'm going to do the math. The opposite of negative 8 is 8 plus or minus the square root. Negative 8 squared, guys, be careful. Negative 8 times negative 8 is positive 64. Negative 4 times 2 is negative 8. Times negative 3 is going to be positive 24. Remember, negative times a negative makes a positive. All over 2 times 2, which is 4. Okay, continuing with those calculations, I would have 8 plus or minus the square root. I have 64 plus 24, which gives me a value of 88, all over 4. Then you need to simplify the radical. You really have 2 simplifications to do here, guys, because you have a radical and you also have a fraction. So I'm going to deal with the radical first. 88 would be, let's see, 4 times 22. And I know that 4 is a perfect square. So I have 8 plus or minus 2 on the square root of 22 all over 4. So I've simplified the radical, but then I also need to simplify the fraction. It may be easier for you to break this apart and write it as 8/4 plus or minus 2 square root 22/4. And I think when you write it that way, it becomes a little bit more obvious that you have things in common. 8 divided by 4 is 2, plus or minus 2 goes into 2 one time, 2 goes into 4 2 times, so I end up with square root 22/2. That answer is acceptable. I would probably leave it that way. There are other ways to simplify it, but that's probably the easiest. And again, I hope you realize you have two answers because you have 2 plus square root 22/2 as an answer, and you have 2 minus square root 2 minus square root 22/2 as an answer. Now, you may be scratching your head going, well, Miss Ralston, how in the world am I going to graph those? Well, to graph that, you're going to have to get an estimate, okay? Those are not, nice, neat, exact numbers. We're going to have to get an estimate from our calculator. Now, since I'm using my daughter's computer, I don't actually have the graphing calculator on this computer. So you can go out to your graphing calculator and you would type the number 2 plus parentheses square root 22, get out from underneath the radical, divide 2, close it, the parentheses, and hit enter. And I get about 4.3. Okay, so when I do the calculations, 2 plus the square root of 22/2, I get approximately 4.3. And then I'm going to turn around and I'm going to type 2 minus square root 22/2. Guys, what I'm having to do when I put this in the calculator is put parentheses around that square root part. So 2 minus parentheses square root 22, out from under the radical, divide 2, close the parentheses, and I get negative 0.3. So I'm getting a rough estimate, and I can use those estimates. If I go back to my graph, we found one at 4.3, so I can kind of guesstimate where that's going to be. Okay, 1, 2, 3, 4, a little bit past 4. And negative 3/10 is going to be somewhere between 0 and -1. So again, I'm just estimating, but it gives me that ballpark figure. And I should get, and I'm drawing a terrible line. Whoops, sorry about that. Get that kind of looking parabola. If I want to find my axis of symmetry, again, remember that axis of symmetry has to go through the vertex. And it corresponds to the h coordinate, which in our case is 2. So the axis of symmetry is x equals 2. Okay, questions related to that second example for quadratic functions? Okay, Do you have any other general questions? Again, I'm going to be looking at your individual exam 2s, and I'll make a recording of the answers, and I'll get your homework for related to quadratic functions posted later on this afternoon. Okay, if not, then I will see you, or at least hear you, on Wednesday, and I'll see if you have questions about our quadratics, and if not, we'll move on kind of to our next topic in the list. All right, I'm ending the meeting and ending the recording, and I will get it posted later this afternoon as well. Y'all have a good day.